All right, part two of our area conversation. We're going to start developing formulas for some other shapes, trapezoids, rhombuses, and kites. That might make your life a little bit easier when trying to come up with the areas of different shapes. And then we're going to talk about similar figures again, get back into that. Okay? But first things first, areas of trapezoids, rhombuses, and kites. And a couple of vocab terms for you. Height of a trapezoid, the height is the perpendicular distance between its bases. Okay, it's the same as it was for the parallelogram. So if this is a base, and a trapezoid, then that height needs to be that distance if you're standing on a base, walking directly towards the other base, so at a perpendicular. Now, it doesn't have to be right there. The height could be here or here, as long as it's at a perpendicular. Okay? Now, the area of a trapezoid is defined by this formula. So it's 1/2 times the height times the sum of the bases. Now, without going into a lot of detail, basically where that comes from is if I took this trapezoid, flipped it over, and added it or slid it over to where it was side by side with this other guy, you would basically get a parallelogram where this is B1 and this is B2. Well, the area of a parallelogram is base times height. So all of this would be the base of the parallelogram, so B1 plus B2, which is why we're adding B1 and B2 here, times the height, which is why the H is in here. But for the trapezoid, we don't want the whole parallelogram, we just want half of it. So that's why we're multiplying by 1/2. So a little bit about where the formula comes from. Mainly just need to be able to use it. For example, in international basketball, the free throw lane is a trapezoid, not the rectangle that we have here. So if we want to find the area of that free throw lane, maybe we're going to paint it, because very many free throw lanes are painted. If you want to find this area, we use the trapezoid formula, 1/2 times the height times the sum of the bases. So the height of this trapezoid is 5.8. It's that distance between the bases. And then we're going to add the bases, 3.6 plus 6. So we get 1/2 times 5.8 times 9.6. And when you multiply that out, you do get 27.84 square meters, and that's how much paint you would need to paint, or now you can figure out how many gallons of paint you might need to paint that lane, that area. Okay? So you see it again, 27.84. Two more theorems here. The area of a rhombus and a kite. The nice thing is the area formula for a rhombus and a kite are the same. It's just 1/2 times the product of the diagonals. Now, why in the world are we using the diagonals? We've been using the sides for everything else. Well, if we didn't know the area of a rhombus, we could just cut this up into two triangles and find the area of that. Now, the base of this triangle is the same thing as the diagonal for the rhombus, and true for the other side over here. Okay? The height is going to be this half of the other diagonal, because remember, diagonals are perpendicular in a rhombus. So by the time we do this triangle and this triangle, we're going to use all of the second base. I'm sorry, all of the second diagonal. So we're using this guy and this guy to find the area of those two triangles. So not too surprising why we're using the two diagonals here. And because it is sort of based off of the area of a triangle, that's the reason why the half resides here. Okay? And same thing for a kite. The diagonals in the kite are perpendicular also. So the diagonals are going to serve as bases and heights for those triangles if we wanted to cut this up into two triangles. Okay? So also why they're the exact same is because those diagonals are perpendicular in both. Okay? Now, also bring up the perpendicular diagonals because we need to remember that they make right triangles in there. And so if ever we need the length of the diagonals or even the sides, we can always use our right triangle stuff, Pythagorean theorem, trigonometry, sine, cosine, tangent, or maybe even special right triangles if it's the right type. Okay? So don't forget about that stuff as well. All right, so let's try to use this stuff. Here's a rhombus, PQRS. Represents one of the inlays on the guitar. Find the area of the inlay. Okay, well, it's a rhombus, so we need 1/2 times the diagonals. Okay, well, how long are the diagonals? Well, diagonal 1 could be this one, which is not 9, it's actually 18, because remember the diagonals in a rhombus bisect each other. And then the second diagonal is going to be this guy right here, which is going to be 24 instead of 12, because again, the diagonals bisect each other. So we need 18 times 12, which is 216 millimeters squared. Quick verification, and that's right. Okay? All right, another example, another use. Okay, and again, where we can kind of go backwards. Okay, the area of this kite is 56.25 square inches. What are the lengths of the diagonals? And what we know is that the diagonal, one diagonal, is 2 times as long as the other. So if we let this diagonal or this diagonal be x, that means that this longer diagonal has to be 2x. Here's your area formula. We know the area is 56.25, which is equal to 1/2 times the diagonals are x and 2x. So one thing I can do is multiply this 1/2 into that 2x. So we get x times x. And then we get x squared equals 56.25. And then we're going to square root both sides. And so x is going to end up being 7.5 inches. Which means that diagonal is 7.5 inches. The other one is going to be 15 inches when you multiply 7.5 times 2. Okay? All right. What else can we do? Actually, this is not on your note sheet, so I'll go ahead and work this out for you too, and then turn you loose on the ones that are in your note sheet. Find the area of this guy. Well, this guy is a trapezoid, so we got to pull out the trapezoid formula. Okay. The height is 4. It's here. Bases are 6 plus 8. So we go 1/2. Half of 4 is 2. I'm going to go ahead and make this 2 times 14. 2 times 14 is 28. So this is going to be 28 feet squared. Just using the area formula directly. Okay? Now, the answer for number 2 is already given here, so hopefully you didn't see it. I'll cover it up here. Try to find the area of this kite really quickly, and then I'll show you the answer in just a moment. Okay, did you get 42 inches squared? This is 1/2 times the diagonals, where 14 and 6 represent those diagonals. So again, we're just directly plugging it into the formula here and multiplying out. Okay? Now, try this rhombus. Find the area, and I think your notes even wanted you to find the perimeter, so try to find that as well. Okay, stop the video, start it back up when you got it, and see if you're right. Okay, here's what you got. The area is just 1/2 D1 times D2, where the diagonals are actually 60 and 80. Remember, in a rhombus, the diagonals bisect each other, so we're going to have to double those. And you should get 2,400 meters squared. Now, to find the perimeter, we have to know the side lengths. Okay, and so we need to go find the side lengths. If this is 30 and this is 40, then we can use Pythagorean theorem because, again, it's a right triangle to find this hypotenuse, which is also the side length of the rhombus. So 30 squared plus 40 squared equals x squared. And when you work that out, you do get 50. So the side length is 50, which means all the sides are 50. So if you want to find the perimeter, just take 50 and multiply it by 4, and you get 200 meters. Okay? Hopefully that makes enough sense. We'll move on to the next section here and talk about similar figures and how areas and parameters and volumes are related. Remember that two similar polygons are polygons that are the same shape but not necessarily the same size. Their side lengths are proportional, not congruent, not equal, right? If they're proportional, then we can write the side lengths as a ratio of A to B, say, and for every corresponding side length, that ratio would remain constant. It's called the scale factor, right? Be equal to the scale factor. Well, if the corresponding side lengths are in a ratio called the scale factor, A to B, then their areas are actually in a ratio of A squared to B squared. So it's actually equal to the square of the scale factor, or equal to the sides squared, and then we write them as a ratio. Y squared, the only thing that I'll offer up to you right now, and if you want more, you can always come talk to me about it, and we can talk about it some more, but it has a lot to do with the fact that to find area, we're multiplying measurements of a shape, whether it's sides, heights, whatever. And so we want to multiply, and so hopefully when you multiply, sometimes you square things is enough to kind of get you to understand that if you're talking about the ratio of the areas, it's always the square of the side lengths or the square of the scale factor. Okay? So again, a couple of different ways to look at it. If we write the ratio of the side lengths of polygon 1 to polygon 2, that ratio is going to be equal to A to B, or our scale factor. If you're going to write the ratio of the areas, it's always the square of that result. Okay? So, perimeters, if we find the perimeter of both of these two figures and write them as a ratio, they're going to be equal to the scale factor also. When we find perimeters, we're not multiplying anything. We're just adding the side lengths. So there's no reason to jump to squaring the sides or multiplying the sides by anything. It's just going to be the same as the scale factor, A to B. Again, the areas is the scale factor squared, or squaring the sides and writing them as a ratio. Now, we're not going to get into solids and volumes right now, but if we were, how do you think the volumes would be related? Since the perimeters are just the same as the scale factor, A to B, the areas would be related as A squared to B squared. What about the volumes? Okay, well, hopefully you're saying to yourself, oh, well, just cube them, A cubed to B cubed, and that would be it. Okay. All right, so let's use this idea here. We've got a couple of questions here. Find some ratios. We know that A, B, C, and D, E, F are similar. We want the ratio of the perimeters, and what we know is that the ratio of the perimeter is equal to the scale factor. So what we really need is just the scale factor for these two guys. And the similarity statement lets us know that BC and EF are corresponding parts. So if we write the ratio of 8 to 12, then we can reduce that down to 2 to 3. And so that's the scale factor. That's the ratio of the perimeters, 2 to 3. Now, ratio of the areas needs to be that scale factor squared, or 4 to 9, right? Or you could square the sides, make this 64 and this 144, and write them as a ratio and reduce it down, and it will reduce down to 4 to 9. Okay? So a couple of different ways you could go about finding it, and there they are. All right? All right, so baking pans. A large rectangular baking pan is 15 inches long and 10 inches wide. A smaller pan is similar to the large pan. The area of the smaller pan is 96 square inches. Find the width of the smaller pan. All right, good. We need some pictures, though. Large baking pan is 15 by 10. Smaller baking pan is, we don't know what the length and the width are, but we know the area is 96 square inches. Well, we can find the area of the big guy, of the big baking pan, just 15 times 10, or 150 square inches. And then we can use the ratio of the areas. 150 over 96, which will reduce down into 25 over 16. That has to be equal to the scale factor squared, right? What's the scale factor? Scale factor is corresponding sides reduced. And since we want to find the width of the small pan, that would be 10 to W, and that's as reduced as we can get. But then we have to square it before we put it down into here. So we go 100 over W squared. Because remember, areas, when you compare them, they're going to be equal to the scale factor squared. Now, cross multiply, you get 25W squared equals 1600. Divide by 25, and 16, that is 64. Square root, and you get 8. And so the width of that small pan is actually 8 inches. Okay? All right. Multiple choice question. You're installing the same carpet in a bedroom and den. The floors of the rooms are similar. The carpet for the bedroom costs $225. Carpet is sold by the square foot, so it's basically based on area. How much does it cost to carpet the den? Well, they're similar. So if it costs $225 to carpet the bedroom, and we need to find out how much it's going to cost to carpet the den. Okay, well, this is based on area, so the ratio is going to be similar to the ratio of areas. In other words, it's going to be equal to the scale factor squared, right? A squared over B squared. Well, the scale factor comes from matching up corresponding sides, 10 and 14. So what that gets us is 225 to x has to be equal to 100 over 196. Or you could reduce that if you wanted to, make your math a little bit easier, and make this, what, 25 over 49. And now you're going to cross multiply this and get 25x equals 11,025, and then divide by 25, and you get 441. So the answer is going to be D. Okay? So again, some uses for these similar polygons. All right? One more to talk about, I think, here, and then I'll let you work on the ones that are in your notes. All right? The perimeter of ABC is 16 feet, and its area is 64 square feet. The perimeter of triangle DEF is 12 feet. If we know that ABC and DEF are similar, find the ratio of the area of ABC to DEF, and then find the area of DEF. Well, we know that the perimeters are going to be of the ratio of 16 feet to 12 feet, which reduces down into 4 to 3. We know that the perimeter is equal to the scale factor, the ratio of the perimeter is equal to the scale factor, and that the area is equal to the scale factor squared. So I've got the area of ABC, which is 64. Don't know the area of DEF, but I know it has to be equal to 4/3 squared, so 16 over 9. And so we cross multiply. right? And we get 64 times 9, which is 576. Then divide by 16. And so the area of DEF is 36 square feet. Okay? That's the ratio of the areas, and that's the actual area of triangle DEF. Okay? All right. Now, in your notes, there are 3 practice problems for you to work on. Go ahead and stop the video and work on those. And when you have all 3 of them done, I'll walk you through how to do those 3, including the challenge one. Okay? So stop it, work them, start this video back up, and we'll see what you got. All right, number 1, the ratio of the perimeters. Well, again, the ratio of the perimeters is just the same as the ratio of the corresponding side. So we can go 18 to 10, reduce this down to 9 to 5. The ratio of the areas is just the scale factor squared. It's going to be 81 to 25. Okay? Very direct. Piece of cake. Now, the TV. A small flat screen TV is 24 inches wide, 18 inches long. A larger TV is similar to the smaller one. The area of the larger screen is 657 inches. Find the width of the large TV. Well, the area of the small is 24 times 18. Which is indeed 432 square inches. So if I write the ratio of big TV to small TV, that's going to be equal to the ratio of their corresponding side lengths squared. Remember, areas are squared. So widths, I need widths. The width of the large TV we don't know, it's what we're trying to find. Let that be x. The width of the small TV is 24, but then we have to square this. So that gets us to 657 over 432 equals x squared over 576, and then you've got some work to do. So 432x squared is equal to 378,432, then divide by 432. So x squared is equal to 876, and then we're going to square root both sides and realize that the width is 29.6 inches. Okay, which again is helpful if you're trying to put the TV in a cubby or someplace maybe over a mantle. I mean, there's definitely some uses for this. Okay. All right, your challenge problem. The Pentagon in D.C., each side of the base is 900 feet. The area is about 1.4 million feet squared. And we're going to make a scale model where the perimeter of the base is 30 yards. So pay attention to the fact that we just changed units. Find the area of the base of the model to the nearest square yard. Okay. So areas. Base to model. Well, the area of the base is 1.4 square feet. 1.4 million square feet. Okay? We don't know the area of the model. So here's what I'm going to do. I'm going to use the perimeter to find that scale factor. Right? Now the perimeters. We need to go base to model. The actual perimeter of the base is this 900 feet times 5 because it's a regular pentagon. Add up all the sides, there's 5 of them that are 900 feet. Over the model, which has a perimeter of 30 yards. Now, this is 30 yards. I'm going to have to convert units. So this is going to be 4,500 feet to 30 yards. Convert these units of feet over to yards. Let's take 4,500, divide it by 3, because there's 3 feet in a yard. And you get 1,500 over 30. Now, you reduce that, and it reduces to 50 over 1. That's your scale factor. So the areas, which is 1.4 million feet squared. Now, if I'm going to turn feet squared into yards, and I want to because we want our answer to be in nearest square yards, I'm going to take 1.4 and divide it by 9. Now, why 9? I know there's 3 feet in a yard, but we're talking about square feet. So 3 squared is 9. So I'm going to take 1.4 million and divide it by 9. Okay? Which isn't typically the way you want to go, because it could give you a decimal. As a matter of fact, it does here too. So, you know what? I'm going to keep this in feet square, and then I'll convert later. All right? So I'm going to keep this in 1.4 million square feet over x has to be equal to 50 over 1 squared. So 2,500 over 1. 1 squared is 1. Cross multiply, we get 2,500x equals 1.4 million. Divide 1.4 million by 2,500. And x is equal to 560 square feet. Okay, that's our units. We want square yards. So again, take 560 and divide it by 9, because there's 9 square feet in 1 square yard, and we get 62.2. They want this in the nearest square yard, so it's just going to be 62 square yards. Okay, a lot of calculation there, but still using the fact that the ratio of the areas is the square scale factor. Okay? All right, that's it. Homework's out in Canvas. Make sure you have that done next time.